Hello, everyone. I'm Zhang from Department of Medical and Molecular Genetics and the Center for Computational Biology and Bioinformatics of Indiana University School of Medicine. Today's topic is about statistical power and sample size calculation for RNA-seq experiment, why and how. So major goal of today's lecture include first an introduction of the power and sample size calculation, and we will go through the several examples about how the biostatistician and the computational biologist do the power and sample size calculation. Start from the background of power and sample size calculation, which is specific for statistical hypothesis testing. So first we have our observation. For example, like a RNA-seq data set collected from colorectal cancer and normal colon tissue samples. And we have a hypothesis to test. It's like GA. If GA is differentially expressed in colon cancer versus normal colon tissue, for which the null hypothesis H0 is GA is not differentially expressed, and the alternative hypothesis H alpha is GA is differentially expressed. So as shown in this table, when the null hypothesis is true and the decision we make based on our hypothesis testing is don't reject the null hypothesis, which is the correct inference, which is also is named as a true negative. And on the other hand, if the null hypothesis is false, there is a differential expression, and by the hypothesis testing, we reject the null hypothesis, which is this means a true positive. That is a correct inference. And also there are two types of errors. Whereas the type 1 error is when the hypothesis is true, but we reject it, which means a false positive. And the type 2 error is the null hypothesis is false, but we didn't reject it, which means there is a differentially expressed genes, but we didn't reject the H0. We consider the gene alpha is not differentially expressed, which is considered as a type 2 error. So the statistical power of a statistical hypothesis test is the probability to reject H0 when H0 is false. That means it's a probability, but it's under the condition that the null hypothesis is false, and the probability to reject H0 makes a true positive inference, which is also equal to 1 minus the probability that not rejecting H0 when H0 is false, which means 1 minus the type 2 error. So by power definition, the statistical power tells you how likely you will detect a real difference or effect, which is the probability to reject the H0 when H0 is false. So 80% of power means you will miss a real effect with 20% of the time. And the statistical power is critical especially for the very expensive experiment. For example, as a clinical trial. So if the statistical power describe if there is a true effect, how likely you will detect it. So in clinical trial, if the drug may really have the effect on the patient, on the disease, but due to the experiment design is not good, so maybe too little patients has been involved. So you didn't. So even the drug has the effect, but you missed the observation based on the derived p-value that is not so significant, that may cause the whole clinical trial fail. And similarly, for mouse experiment, so when people conduct a mouse experiment and you spend a lot of time to wait for the mouse, to wait for the experiment, and but this is highly common that if the mouse number is not that high, even there is a true effect, we don't know. It's unobserved. No one knows if the effect is true or not. But even when the effect is true, but due to the experiment, the experiment setting doesn't enable enough power, you will commonly observe a very annoying p-value like 0.06. And similar for RNA-seq experiment. Before we go to the specific discussion of the power analysis for RNA-seq data for RNA-seq experiment, we first go through the how the statistical power is computed via t-test example, and illustrate what factors may determine the computation of statistical power. So here's the example of a student t-test. So there are two types of t-test. One is one sample t-test, which tests if the mean of series observation is equal to a pre-given value or not. And second is a two sample t-test. It tests if the mean from the observation of two groups that are equal or not. And this is the t-statistics used for one sample t-test and two sample t-test. We will use the two sample t-test as an example to show how the statistical power of t-test is computed. You can imagine here x1 is the gene A's expression collected from a series of colon cancer samples, and x2 is the expression level of the gene A collected from the normal samples. And here x1 bar and x2 bar just shows the mean of the expression level of gene A in the colon cancer and in the normal colon. And this part is the pooled variance. So here the hypothesis 0 is that the mu1 equal to mu2, which is the x1, which is the mean of the expression level of gene A equal to the mean of in the colon cancer equals to the mean of the expression level of gene A in the normal colon. And the alternative hypothesis is they're different. So the t-test approach is that under the null hypothesis H0, so we assume mu1 equal to mu2. So the distribution under the hypothesis, the distribution of the x1 minus x2, x1 bar minus x2 bar follows a t distribution with mean 0, which is the red curve shown here. And this screenshot shows an example of t-test power calculator. So under the hypothesis, we can have this curve computed, and the two-tail probability of observing x1 bar minus x2 bar can be computed. So for your observed x1 bar minus x2 bar, you can compute at least through over the curve, and you can compute the probability, which is the p-value. And with a pre-given significance level alpha, here is shown and showed by here, which is the type 1 error, and which is the type 1 error and the p-value cutoff. If the p-value is smaller than alpha, your observed p-value is the p-value of your observed x1 bar minus x2 bar is smaller than alpha, we will reject H0. This means if the observed x1 bar minus x2 bar is on the right side of this green line or on the left side of this green line, we will reject the null hypothesis. So with this information, can we determine the power? Actually not. This just shows how the statistical test works. Please keep in mind that the statistical power shows the capability to reject the null hypothesis when the null hypothesis is not true, is false. So we need to describe how, based on our assumption or prior experimental information, how x1, x0 is not true. So here, there's another line, it's a blue line, blue curve, is the distribution of x1 minus x2, x1 bar minus x2 bar, which needs to be derived from prior information of x1 and x2 or experimental assumption, like the mean or variance, including the mean or variance of x1 and x2. And here, the power is what? Power is 1 minus beta. Since beta here is the type 2 error, you can say this is under null hypothesis, the red curve is under null hypothesis, the distribution of the x1 bar minus x2 bar. And the blue line is the alternative hypothesis. It's based on our prior knowledge, we derived the distribution of x1 bar minus x2 bar. So we can say if the line and alpha is the significance cutoff, and if the difference between, if the value of x1 bar minus x2 bar is on the right side of this green line, we will reject h0. So here the blue part beta is the probability that x1 is not equal to x2 based on our prior knowledge. And the difference between x1 bar minus x, the difference between x1 bar and x2 bar, or the value x1 bar minus x2 bar, is on the left side of this curve, which will not be rejected, because we say on the right side of this curve it will be rejected. So the beta part is exactly the type 2 error, and the right side of this blue curve is the statistical power, which is 1 minus beta. So here, we demonstrated that the power is the 1 minus beta, and when we talk about what factors may determine the power of a t-test, first we can very intuitively we can say is the difference between x1 and x2 can directly determine the power. So if x1 is more different than x2, based on our prior information or our assumption that this blue curve will be further away comparing to the red curve, that the beta will be smaller and we will get higher power. Second is if the mean, if the variance of x1 and x2 are small, this may cause the two curve, the pooled variance is smaller, and this two t distribution will be narrower. And second is the distribution between x1, and the second is about the difference, and the second is the significance level. If the alpha, if we go for a larger level of alpha, we can put this green line to the left side, which will also give us smaller beta and higher power. But the issue is that with doing this, we will increase alpha, which is a type 1 error, and will increase the p-value cutoff. And the last one is the sample size. So because this one, the curves are the distribution, shows the distribution of x1 bar, the mean of the difference between the mean of the observed x1 and the mean of the observed x2. So the variance of the mean is equal, the standard deviation of the mean equals to the standard deviation of the value divided by the square root of the sample size here. So we will get the sample size n. So if we have a higher sample size n, the variance of this two curve x1, the variance of x1 bar minus x2 bar will be smaller, and we will get a smaller beta here. So we note here that the difference between x1 and x2 and the significance level alpha and the sample size may all contribute to the samples, to the power. So, but normally when we do the power calculation, the statistical significance are fixed, and our prior knowledge of x1 and x2 are fixed. So we will have the sample size n varied, and with the sample size n varied, we can determine the power. And also with and vice versa, with the power varied, we can determine the n. So this is a common statement of the statistical consideration of the biostatistics made for the power and sample size calculation. So there will be 6 treatment groups: drug A, drug B, drug C, and their combinations, each of which will be with a vehicle control. And the major outcome variable is tumor size compared between each treatment and control group. We anticipate that the vehicle only treated mice will have tumors from start to finish, and the drug treated mice will have tumors at the onset of treatment, but will have reduced post-treatment tumor size and number. This is the object. And given the considerations, the following sample size and power calculations will be measured. There will be 6 independent comparisons and 6 treatment group versus corresponding control group. Therefore, in testing each of the following animal study points, there will be 5% divided by 6 equal to 0.83% type 1 error is controlled per comparison. This is a type 1 error. We fix a type 1 error here with the consideration of multiple testing p-value adjustment, which will be included in another lecture. So our preliminary data suggested that the tumor size has a coefficient of variation of 50%. And 12 animals per group will allow us to detect the 57 tumor size reduction with an 80.7 power. So here, the 0.87% type 1 error is the statistical significance level, which is the alpha type 1 error level. And coefficient of variation and the tumor size reduction, these are based on our prior knowledge or our assumption to the experiment about how the difference of the tumor size will be between drug treated and the non-drug and vehicle controlled subgroups. And then with this value fixed, and we will student t-test in testing the tumor size change, which the statistical test fixed, we can compute 12 animals per group will give us 80.7% power. So this is with these factors fixed, and we will have the with a fixed number of sample, we can compute the power, and with a fixed powers, for example, like more than 80% of power, we can compute the minimum number of animals can guarantee this power. So then we talk about the power and sample size calculation specific for RNA-seq data. Like we have mentioned that the key factors including the object and hypothesis test, which for RNA-seq data, so there are different types of statistical tests, including like D-seq based differential gene expression test, which use negative binomial distribution, IGR-based differential gene expression test, which use Poisson distribution with over dispersion assumption, and also survival analysis, which use the log rank test. So we have prior knowledge of and also we have different prior knowledge of the experiment. So for RNA-seq data, so the prior knowledge can be more complicated than mouse experiment due to we have more genes, and each gene may have its distribution, its mean, its counts, the number of counts observed, the over dispersion level, and also their variance, and also the common methods may need to upload a similar data sets and assess the parameters for the as the prior knowledge of the experiments via simulation. So, and also another thing is about significance cutoff. Like I mentioned, there's we need to consider multiple test p-value adjustment. For RNA-seq data, for example, there are 20,000 genes, around 20,000 genes, and with a p-value 0.05 by Bonferroni p-value correction, the p-value will be 0.05 divided by 20,000, which is very small. So this directly gives us the intuition that with using RNA-seq data, so and with considering multiple tests for discovery control, the type 1 error we can use is very small. So normally the power for test of fixed genes differential expression is very low. That suggests the RNA-seq data is not suitable to confirm the differential expression change of fixed genes. Instead, we'll use PCR experiment. But for RNA-seq data, we are more focusing on the whole genome level, pathway level change. Then also, same as the power compilation illustrated by the t-test experiment example. So with fixed power, we can compute sample size. With fixed sample size, we can compute the power. And this here I would like to illustrate several examples of how RNA-seq data power of the RNA-seq data power calculator. So since it's really hard to detect a single differentially expressed gene with a good power, with a high power, so we can compute the power to detect the top K differentially expressed gene. So the idea is like with prior information derived from other prior data set, and with certain parameters we set here like FDR level, the ratio of normalization factors between two groups, and the number of genes for testing, and also some the minimal fold change of the expected number of prognostic genes. Here, the prognostic genes are the differentially expressed genes actually, and also the genes expression parameters. We can compute a certain power to detect the top detect the top 100 differentially expressed genes. So for example, if we change it to 50, it will show how many samples, RNA-seq samples, we may need to detect the top 50 differentially expressed genes with a power of 0.8. So normally when we use when we do in the power calculation, we will use the 0.8 as a good criteria. This is a second RNA-seq data power calculator. It's called S size RNA, so which is a R package. So both of these the two power calculator introduced here are for the EdgeR. So our EdgeR based differential gene expression test. So here instead of testing instead of calculating the power for the top K differentially expressed genes, here this method, this package specifically compute the power for each gene, for the power to derive a certain fold change for the differential gene expression with the vector, the number of with pre-given fixed dispersion level and the mean counts of each group. So from these two examples, we can see that these two different mechanisms are these two different methods are all for the EdgeR based differential gene expression test, but they are with very different assumption, and we need a different set of parameters. So one thing I would like to talk here is that with knowing how the power is computed, so this illustrated here, but we can see that the statistical power, first, the statistical power described the capability to detect a real effect, and which is we have seen that which is highly object and statistical model dependent. And the power calculation relies on the known model, prior information, and significance level. With this information fixed, and with fixed power, we can compute the sample size. And with fixed sample size, we can compute power. So the key thing I want to convey here is that, so you can see, so for different statistical tests, if we set the model and set all the parameters, compute the power is pretty simple. But the key difficulty is that how to determine the most proper statistical test, and how to derive for some very complicated case, if there is no well-written algorithm or tools for power computation, biostatistician will derive the specific functions to do the power calculation, and also different to a differential gene expression test. For a differential gene expression test, if we use two similar but different methods, it may give us some similar results. But for power calculation, if we just make a wrong assumption or made a wrong parameter in, so the computed power or sample size can be totally misleading. So that's why, so for the power calculation, so normally for a complicated case, we need to specifically go to a biostatistician to make a consulting. That's all of the materials I want to introduce today. Yeah.